Hello everyone. Welcome to the live interactive session on geology and soil mechanics. So, today we will be uh, discussing about the basics of soil mechanics, and then as the course progresses along the 12 weeks, we will be revising whatever will be discussed in the your main lectures. Those two will be discussing, and then simultaneously we will be solving some simple problems together. Okay, so what I suggest is that you also try to solve the problems yourselves while I solve for you. So that way it will be a good practice for all of us. And before I begin, I would like to welcome you all to this course once again. And I am Ashish. I am a final year PhD candidate at IIT Kanpur. I completed my bachelor's from NIT Silchar in 2020, and then I directly joined IIT Kanpur as a PhD student after my BTech. And yeah, and so hopefully I will be completing my degree this year, right? And over that, I am a Prime Minister's Research Fellow at IIT Kanpur from August 2022. Okay, so uh, in the run of this course, if you have any doubts or confusions, please feel free to ask me. I will try my best to solve them, and if not, I will look for some sources and then try to solve those doubts, or I will forward those to the course instructor. And uh, this course is the basic and the primitive course in soil mechanics, the main introduction, the course which introduces you to soil mechanics. So generally in bachelor's, I think it's taught in your third or fourth semester, probably. It's taught in third or fourth semester as far as I can recall, and this introduces you to the field of geotechnical engineering. Right. So even though the name of this course is Geology and Soil Mechanics, you will see that we won't be much bothered about the geology part, right? We will be more focused on the soil mechanics portion. Okay. So initially we will start by uh, seeing how mechanically we can define a soil, and then we will see some basic properties, and from there we will like progress the course. Then we will learn about how to classify the soil. Then we will learn about some properties such as consolidation, then shear stresses. All right, so all those things we will study in this 12 weeks. Okay, so there will be 12 discussions session or live interactive sessions of 2 hours each. Okay, so 24 hours in total, and and at the end we will be having a 1 hour long sum up session just before your exam, so that we can, in 1 hour, we will just glance through or skim through whatever we have studied in this course. Okay, so this is how we are going to progress, and so this is relatively easy course, and it should be easy on you too. The assignments, please try to do the assignments on time, and solve all the questions of the assignments on time, which will be benefiting you in your main exams. For those who are, obviously, for not for all, for those of you who will be taking the exam, uh, those will be beneficial to you. And apart from me, there is one more course TA. Okay, I don't know actually who is that, but you have one course TA. Yeah, voice is breaking, maybe because of the internet. Okay, so as I was saying, that apart from me, you have one course TA2 in this course. So the course TA will be handling your assignment questions, grading of your assignments, grading of your exams, and all those stuff. He will be handling that, and if you can find the details of that in your course portal itself, I guess. And you can contact, you can also, yeah, also one more important thing is that if you have any discussion, you have one discussion group. okay, Google discussion group, that we will get the access from your in from the NPTEL portal itself. Okay, so if you have any doubts, you can write your doubts there, and the course instructor or my course instructor or the course T or myself, whoever is available, will try to answer your question. All right, they will try to answer your question. And apart from that, yeah, as I said, there will be assignments. Please try to solve those assignments, and at the end, uh, he will be for those who will be taking an exam. There will be an exam. So the final grading will be done based on both the final exam and the assignments, right? Okay. So today's whatever we are going to discuss today is nothing but whatever is already discussed in the main lecture, whatever video was posted in the NPTEL portal. So we are just going to revise that a bit, and revise whatever was discussed, and then we are going to solve some basic easy problems. Okay, and in the meantime, if you have any doubts, you can ask me. If it's possible, I will try to, obviously I will try to solve them. Okay, so let us begin. And one more thing, I wanted to ask that, like, are all of you students, or my? I'm obviously all of you are not students. Some of you might be working also, right? So some of you might be in industry. Okay, right? So I think this time 6 to 8 is fine, because you can join after your office hours also. Okay, for the discussion sessions. And so every Monday we are going to have this discussion session for 2 hours. And in February, towards the end, and in the beginning of beginning of March, or in the beginning of March probably, there will be some interruption, because I have to travel somewhere. So there will be some readjustment of the dates, but nonetheless we will be having total 12 plus 1 13 sessions. But some readjustments of the day or the dates will be there, that will be uh, that the team will let you know in due course of time. So keeping all that aside, let us begin with today's session. Okay, so the first question obviously is, what is soil, or how is soil formed, right? So how is soil formed? The soils are basically formed from where? Rocks, right? Right, the soils are, from where is soil formed? Soil is formed from rocks. So what happens is that rocks undergo disintegration. Disintegration, how it undergoes disintegration? Weathering, weathering, then in the effects of wind, weathering such effect of wind, then chemical action and all those stuff. Due to that, what happens? Rock weathers, or rock disintegrates. Due to the disintegration of rocks, what happens? Soil is formed, right? And rocks are also of different types, right? So what are the different types of rocks? We have igneous rocks, we have sedimentary rocks, and we have metamorphic rocks, right? So what happens due to weathering? Okay, so chemical, both chemical action and mechanical action. Due to both chemical and mechanical action, what happens? From rock we get soil. Okay, so these things are basic, very basic, and I'm not going to repeat that much. All right, so these were already discussed in the class, right? So let us not waste time in this. And right, so there are soil types. As you have studied, there are soil types. So what are the soil types? You have residual soil. Residual soil means, so rock is formed at one place. Rock is formed at one place, and due to weathering or disintegration, the soil also remains at that place only. So that is residual. Then we have transported. So after the disintegration, the soil gets carried from one place to another. And how can that get carried? So there are various agents. Agents can be wind, right? Wind can carry soil from one place to another. Then you have the action of water. Rivers can carry um, soil from one place to another. So all those things. Okay, so this is how soil is formed. Okay, so let us not waste our time much in this. Okay, that is this. It was discussed in detail in the main class, right? So now, so from here, our basic mechanics of soil starts, right? So what is soil? So soil can be defined as a three-phase system, right? So what do you mean by three-phase system? Three-phase system means there are three main components which forms a soil mass, right? Three main components which forms a soil mass. Say you go outside and take some soil in your hand. The amount that the soil that you have taken in your fist, that soil is composed of three parts. We have air in it because obviously it's not completely dense compacted, so there will be some air inside the void spaces. Okay, okay, there will be some water, it might be moist, the soil may be moist, so that case you will have some water, and obviously at the end you are going to have the soil solids. Okay, the soil particles, individual soil particles which form the soil solids. So that's the way how we can define the soil as a three-phase system. So we have air, we have water, and then we have the soil solids. Okay, okay, so these are the what, these are the soil grains, and in between we have the void spaces, right? In the void spaces, now the void spaces can be empty means it will have air. Okay, either that can be the case, either the voids can have air, or the voids can have water, or some voids can have air, some voids can have water, right? So this can be the case. Now if all these voids in the what, in the soil mass, all these voids in the soil mass are filled with water, then we call the soil as a fully saturated soil. Okay, then we call the soil as a fully saturated soil. And if all the voids in this soil doesn't have water, it just has air, then we call this as a dry soil, right? No water, we call it as a dry soil. And third case is that it has some voids of water, some voids of air, then we call it as a partially saturated soil. Okay, now now so as I said, air, water, and we have soil solids, right? Now all these components will have individual weights, right? So we have weight of soil solids, we can write as ws. Then we have weight of water. So will air have what, will air have any weight or not? Will air have some weight? No, right? Oh, okay, mic is moving. uh, wait, I will try to hold the mic with one hand because I have to see what's there na? Just a second. Yeah, yeah, so as I said, the soil solids will have some weight, right? The soil solids are going to have some weight. Then you have the water that is going to have some weight, and the air, will it have some weight? No, there is no weight of water, no weight of air, right? So zero, nothing. Then the soil solids will occupy some volume, that is vs. Okay, we can write it as vs. Then the water will occupy some volume, that will be vw. And the air is also going to occupy some volume, that will be va. Okay, now what is the total volume of the soil? Is composed of the volume of the soil solids plus volume of the water plus volume of the air. Now what is the total weight of the soil? That is weight of soil solids plus weight of water, right? There is no weight of air, air is weightless, we can consider air is weightless, right? Now the volume of water plus volume of air, these volumes are where, these are the volume, that is the volume the voids, right? Because air and water will occupy void spaces only, so this we can write as volume of voids. Okay, this we can write as volume of voids, right? Now, why defining these volumes and weights are important is that we need to define some basic properties known as index properties based upon these quantities. Okay, so what are index properties? So in so there are two kinds of properties. There are tests. So one test is that there are some tests which we do to classify a soil. These are known as classification tests. So say you take some soil in your hand from here in India, and then you take some soil in your hand from say Japan. So how do you how will you call and tell your counterpart in Japan that I have this kind of soil? I have this kind. So you need to quantify the type of soil, right? You need to quantify the type of soil. In order to do that, you need to classify the soil. You need to classify the soil. And in order to classify the type of soil, what you need to do is that in order to classify the type of soil, what we need to do, we need to do some tests. You need to do some tests. Now, the numerical results that are obtained on the basis of such tests are called the index properties of soil. So the index properties of soil are actually some properties or some new values of some numerical properties that will assist us in to numerically to classify the soil. Okay, to classify the soil. So soil classification we will study in detail. Okay, there we will discuss how to classify the soil in detail. We will do that in the future classes. In detail we are going to solve any examples also. We will take some examples and we will solve, we will see how we can classify different types of soil. Okay, now there are different types of index properties, right? So there are different types of index properties. Just a second. Yeah. There are different types of index properties, as I said, and these index properties are defined based on the volumes and the weights that we discussed just 2 slides back, right? So let us see what is water content. Water content, water content is nothing but weight of water by weight of solids into 100%. Now, please tell me, okay, please tell me what will be the what is the lower limit of water content? What is the lower limit? What is the minimum value of water content that any soil can have? Zero. Right, correct. Prithviraj, correct. Minimum value is zero. Okay. And what is the maximum water content a soil can have? What is the maximum water content a soil can have? Yeah, correct. There is no limit. Okay. There is no limit. Okay. So we have a lower limit of zero, but there is no upper limit in water content, right? Zero means the soil is dry. Zero means the soil is dry. Next. So next we have what? Void ratio. What is void ratio? Void ratio is volume of voids by volume of solids. Okay, volume of voids by volume of solid. Now similarly, what is the lower limit of void ratio? What is the lower limit of void ratio? Again, the lower limit of void ratio is also zero. Hypothetical situation where soil has no voids. And similarly, similar to water content, there is no upper limit. Okay, there is no upper limit. Next we have porosity. Porosity is also similar to void ratio, but the definition is a little bit different. It's volume of voids by total volume. So void ratio is volume of voids by volume of solid. Porosity is volume of voids by total volume. Okay, so into 100%. Okay, so what is the upper limit of porosity? Upper limit and lower limit of porosity. What are the upper limits and lower limits? First, let us discuss about the lower limit. So what will be the lower limit of porosity? 0, correct, Irfana, correct. Lower limit is 0. And what is the upper limit? Yeah, about correct, correct, 100%, correct, correct. All of you are correct. It's 100. Okay. Next we have what? Next we have the degree of saturation. So what is degree of saturation? Degree of saturation is volume of water by volume of void. So in the void, how much is water and how much is air? That defines saturation. If the whole void is, so we have volume of voids and volume of air and volume of water, right? And this completely forms the volume of void. Now in this volume of void, how much is air and how much is water? That defines the degree of saturation. If it is totally the volume of voids is it's taken by water, then it's when the saturation is 1, right? Then means the soil is fully saturated. And if the volume of water is 0, that means the whole of the volume of void is taken by air, that means the saturation is 0. Okay, this is dry soil. So volume of voids by volume of water by volume of voids. Okay, again, if you want to express in terms of percentage, minimum is 0, maximum is 100%. Okay. Okay, next we have air content. Okay, air content is quite similar to your this uh, degree of saturation, but here we have air, volume of air by volume of voids, which I can write as 1 minus the degree of saturation. Then we have percentage air voids Na, can write it as volume of air by volume into 100, total volume into 100%. Okay, next you have unit weight. Unit weights, the first is the bulk unit weight. Now what is unit weight? Unit weight is what? Weight per unit volume, right? This is what unit weight is, weight per unit volume. So the bulk unit weight is written as gamma T or gamma B. Generally it is written as gamma T or total unit weight. Okay, total unit weight. This is the total weight by total volume. Okay, that means weight of solid plus weight of water by volume of solid plus volume of water plus volume of the air. Okay, that is volume of solid plus volume of voids. Okay, this gives you the bulk unit weight. Now what is dry unit weight? Dry weight is nothing but only the weight of solids you are taking now. Weight of solids by total volume. This is the dry unit weight. Okay, this is the dry unit weight. Okay, so next we have the saturated unit weight. This is the sigma sat. Is the saturated weight, means when the voids are completely covered, taken over by water, filled with water by total volume. Then we have submerged unit weight. This one is or sub equal to the submerged weight by total volume. So what does submerged unit weight means? Means see, say um, you submerge any object in water. So what is going to happen? You will have a upward buoyant force that will be acting on that object, right? Due to which the effective weight of that object is going to reduce, right? Due to the buoyancy. So that weight is the effective weight is the submerged weight. Submerged weight divided by the total volume. This is going to be the submerged unit weight, and I can also write it in terms of the saturated unit weight minus gamma W. Gamma W is nothing but the unit weight of water, which is taken as 9.81 kilonewton per meter cube. Okay. Yeah. So then we have unit weight of solids. Similar solids by volume of solids. That's the solids you are taking. Okay. Then we have specific gravity of solids, which is GS. Okay, which is GS. specific gravity of solids is Ws by Vs into gamma W. Now, what is the definition of specific gravity? Is the weight of that object, weight of that substance divided by the weight of equal volume, of water, right? Weight of, if I want to find out the specific gravity of this pen, what I will do, I will measure, this pen, I will measure the weight of this pen, and then I will submerge it in water, and I will see how much volume of water it displaces. Okay, I will submerge, I will put this in a glass, say, and then some water is obviously going to spill out of the glass, and I will measure the volume of that water. That will give me the volume of, okay, volume of this pen, right? So weight of solids divided by the weight of equal volume of water. Okay, weight of equal volume of water, this gives us the specific gravity. Okay, so ws is the ws is the weight of solid, and vs is nothing but the volume of solids times gamma w is going to be the weight of that volume of water. Okay, that is nothing but the specific gravity of solids. Okay, and this also I can write it as C gamma s by gamma w, right? So these are the basic numerical parameters that we generally use, okay, to quantify different things related to the quantify different properties or classify the soil. Okay, classify the soil. Next, you have the grain size distribution curve. Okay, what? Oh, okay, how many? So, do you have any idea what do you mean by the grain size distribution curve? Any one of you? What do you mean by this grain size distribution curve? What do you mean by the grain size distribution curve? What do you have in the x-axis and what do you have in the y-axis in this curve? Curve means obviously you are plotting it somewhere, right? So you will have one x-axis and you will have one y-axis. So what do you have in the x-axis and what do you have in the y-axis? That is the question. To determine the size. No, I must, yeah. Diameter in x-axis and percent fine. Yeah, diameter means the soil particle size. Correct. The size of the soil particles, you can also turn on your mic and speak. Okay, there is no issue in that. If you want to write, you can write obviously in the chat, and if you don't want to write, you want to speak, you can always turn on the mic anytime and speak. Okay, there is no boundary in that. Okay, this is not any formal class or something. Okay, it's very informal. Okay, so please feel free to stop me, speak with me, anything you want. Yeah, so in the x-axis we have the the particle size, and in the y-axis we have the percentage final. Okay, percentage final. That's how we get the grain size distribution curve. Okay, so we have a graph like this. Here we have the size of particles, say in millimeters, and here we have the percent finer. Okay, now what does it mean? So we will have some graph like this. Okay, we will have some graph like this. So say this like this, we will have, say, particle of size, say 5 mm, and we have percentage finer, say 70%. That means 70% of the particles that form the soil mass, 70% of the particles that form the soil mass are having a size that is less than what? Less than 5 mm. Okay, this means this is what it means by percentage final. Now, how do you get this grain size distribution? So this grain size distribution curve is very important for soil classification. We will see that. Okay, when we classify the soils later, we will see why this grain size distribution curve is important. Okay, so how do you get this case? How can we get the, say I go out and you go out, remember the amount of soil you have taken in your fist. Okay, so if you want to find the grain size distribution of that soil, how do you do that? What is the method to determine the grain size distribution of that soil? How do you do that? How do you determine the grain size distribution? Yes, sieve analysis. Correct. Correct. So we need to do the, yeah, correct. So we need to do the sieve analysis to determine the grain size distribution. So what is sieve analysis? Sieve analysis is nothing but you take the soil, you have graded sieves from 80, from sizes 80, 20 mm, 10 mm, 4.75 mm, like this. To arrange your sieves in order. Then you take then you take a soil of known amount of weight in your weight, and then you put it in the sieve and start shaking. Then what is going to happen? The soil is going to flow down the set of sieves, flow down the column of sieves, and that's way you are that is the way you are going to get the weight that is retained on each of the sieve. Okay, the weight that is retained on each of the sieve. Now that weight divided by the total weight will give you the amount of weight that is retained on each sieve, right? Okay, that weight divided by the total weight into 100 will give you the percentage of weight retained on each sieve, right? Now that percentage minus 100 is going to give the percentage finer. That is the percentage of weight that is finer than that size, right? Very simple. So what we do, we yeah, so we have sieves of different sizes arranged in column like this. We have sieves that are arranged in a column, and then we put the soil of known mass at the top, and then we put it in the sieve shaker. Okay, then we shake it, and then we measure the weight of soil that is retained on each sieve. Okay, so what are the general size of sieves? The size of sieves are 80 mm, okay, 80, 20 mm, 10 mm, 4.75 mm, 2 mm, like this. We will go to 75 microns. Okay, 80 mm to 80 mm to 75 microns. Okay, this is the gradation of the sieves. Okay, this is how you arrange the sieve. Okay, so what is, as I said, what is required to be done to get the grain size distribution curve? Do the sieve analysis and or hydrometer analysis. So for coarse soil, okay, so for soil, say sandy soil, okay, sandy soil is very granular soil. The size of the particles are expected to be not that less, right? Mostly greater than less than 4.75 mm, but greater than 75 microns, right? In that case, what we can do, we can just go for the sieve analysis. Okay, we can just go to the sieve analysis. Now say you have a clay soil, it is a fine grained soil. So clay soil that is clay, by clay soil I mean the soil that you can mold. Okay, okay, you can mold, or somewhere, you know what is the difference between a sandy soil, you can visualize that, right? When I say clay soil, you can visualize that. Okay, so you know what is clay soil, how like you have some a picture in your mind. So obviously clay soil are going to have soil size, particle size very less particle size. So for that, what we need to do, we need to go for the hydrometer analysis. Okay, for that we need to go for the hydrometer analysis. So for the fraction of soil that is passing through 75 micron, what we do, for that amount of soil we do a separate analysis known as the hydrometer analysis. That is known as the hydrometer analysis. So for 80 to 75 micron, you can do the normal sieve analysis, and for the soil which is soil size having size less than 75 micron, we take that soil mass and do the hydrometer analysis. Okay, we can do the hydrometer analysis. Now let me just write the table for sieve analysis. Okay, so first we have the what, sieve size, Okay, it begin from 80 mm like this, it will go to 75 micron. Then we have the weight retained. Okay, then we have cumulative weight retained. Okay, then we have, you can find out the percentage finder. Okay, so like this we can make one table, and from this what we can do, finally we can plot the percentage finder in the sieve sizes to get the grain size distribution curve. Now say, as I said, if the soil is a fine grained soil, what we have to do, we need to go for an additional analysis known as the hydrometer analysis. Okay, we know it known as the hydrometer analysis. So this hydrometer is a device that looks something like this. It is generally made up of glass. It is a glass device. It is made up of glass, and it is a bulb at the bottom, and it is a narrow neck, and then it's a long this tube like thing, and then at the bottom it is a bulb. It is a bulb. Okay, so this is how the generally a hydrometer looks like. Okay, so you can go in YouTube and you can search for hydrometer analysis, you will get n number of n number of videos there, you can have a look. Okay, so in hydrometer analysis, what we do, remember the amount, the soil that we have taken, that has passed through the 75 microns sieve. We have that amount of soil that has passed through the 75 micron sieve. We take that soil and then we make a solution. So we have a long beaker, long flask or volumetric flask or a beaker, where what do you do is that we put that soil, and when we make a solution with with the distilled water. So we take the soil, we pour distilled water in it, and we make a solution. So there will be some turbid solution will be there. Okay, in this long graduated flask there will be a turbid solution formed with the soil particles passing through 75 micron and your distilled water. So why do you use distilled water? Is that distilled water is used in hydrometer analysis because distilled water does not have ionic properties. Okay, doesn't have ions in it, ionic properties. So what happens, if there is ionic property in the water, what is going to happen, it is going to make those tiny soil particles charged. And if the soil particles get charged, so some particles will get positively charged, some particles will get negatively charged, and then what will happen, the soil particles will stick to each other. The soil particles will stick to each other to form a larger soil particle. So that we do not want. We want that the soil particles remain individually separated. Okay, individually separated. So that's why we what we do is that we use distilled water. So then what we do, then we put the so will it make the soil cohesive? What will make the soil cohesive? I didn't understand. What is going to make the soil cohesive? Normal water, you are saying. If you pour normal water, yeah, kind of, no, yeah, kind of like, yeah, you are right. So what happens if we put normal water? The particles are going to stick with each other. Okay, the particles are going to stick with each other, and that is going to give us the wrong values, because in that time you will be measuring the values for a larger particle size. The actual particle size you won't be able to capture. Okay, that's why it's very important that we use distilled water. Okay, and then what we do, then we put the hydrometer in this solution, in this flask. Here we put the hydro we uh, just a second. Yeah, just a second now. Yeah, so then what we do, then we put the hydrometer here. Okay, hydrometer here, and then we take the reading of the at the neck. Okay, at this part we take the reading, that is the RH. Okay, this RH is nothing but the effective depth. It is called the effective depth, and we keep on taking the reading. So we have time and we have RH. Okay, so at 0 second, so you put the solution, you just put the soil in the flask, you put distilled water, you mix the solution properly, you mix it, and then you place the place the what you do after mixing, you put the hydrometer in the solution. As soon as you put the hydrometer in the solution, your clock starts. So at 0 time, when time is 0, you need to write down the reading. Then say at 10 seconds you need to write that, then 20 seconds you need to write that, in 40 seconds you need to write the reading. Okay, 80 seconds like this you need to keep on noting down the reading, say for 12 hours or 24 hours, like that. Okay, so up to 1 hour you will do, then 1 hour, after 2 hours, and after 2 hours you will take, next 4 hours you will take, then after 8 hours you will take, then after 16 hours you will take. So like this you need to take the reading. Okay, so essentially what you are doing is, what the hydrometer is doing is that it is relating the time to this RH. It is the hydrometer, this effective depth, and this effective depth is nothing but the representation of the density at this point, density at this point of the soil suspension. Okay, it until find actually measures the density. Okay, so this the main basic principle behind is the Stokes law and all those things. I am not going to detail, so you can get it in any standard textbook, and I think it has been discussed in the class also. So the main principle with which this hydrometer works is the Stokes law. Okay, Stokes law. Now now you take this reading RH, right? This reading RH, this reading RH is very sensitive, and it needs to be calibrated. Okay, it needs to be calibrated. So the corrected hydrometer reading is nothing but RH plus Cm plus minus Ct and minus Ct. Now what is Cm? Cm is the meniscus correction. So the soil solution that you are having in that flask, that is very turbid, right? Very turbid or opaque kind of thing, right? It will be very opaque. So you cannot clearly note down the lower meniscus of where the water is touching the you cannot actually load down the see the lower meniscus of where the water is touching the your graduated neck on the hydrometer. So what you do, you take the upper reading only. Okay, but actually what we need to, you need to take the lower meniscus reading. Okay, meniscus reading. So what we do, we apply some meniscus correction, which is always positive. Okay, we will always, that will be always positive. Okay, after that we have the temperature correction. So if the temperature of the water increases or the solution increases or decreases, you know that is going to affect the density of the water, right? So if the temperature, so for that reason we have a calibration chart. Okay, we have a calibration chart, and hydrometers are generally calibrated at room temperature of 27 degrees Celsius. If the temperature is more than uh, the or the calibration temperature, what we need to do, we need to add the temperature correction, and if it is less than the calibration temperature, you need to minus the correction. Okay, that is all. And finally we have the dispersive agent. So when you put the make the solution, make the soil solution along, we have to take care of two things. One is that I said, you have to use a distilled water, and second is that you have to use a dispersive agent. The dispersive agent will again make sure that the soil particles do not stick to each other. But this dispersive agent, or there is some powder which you need to put, or some solution is that you need to put in that soil solution, that is called the dispersive agent. Okay, the dispersive agent makes sure that this tiny soil particles do not stick to each other. Okay, but this dispersive agent itself is going to disturb the density of the soil a little bit, the composition of that solution a little bit, disturb the not the soil, the solution, soil solution. The dispersive agent is going to disturb the density of the soil solution a little bit, right? So for that we need to make a correction that is known as the dispersive agent correction, the CD. So we always subtract that from the RH. Okay. So finally, if we do that, we will get the get our corrected hydrometer reading. Okay. So from RC, we find the effective height, effective depth HE, which is actually given in form of a calibration chart. With this calibration chart is given with the instrument from the manufacturer. So with that you can relate, and from there we can find the HE, this HE effective depth. Then from the effective depth you can find out the diameter. Okay, there is one relation that we get from Stokes law, okay, which relates the diameter to the HE and the time and all those things. Okay, so finally, so remember you had noted RH. From RH you find RC, from RC you find HE. Okay, now using HE and time, from using HE and time you can get the D's, diameter size. Okay, diameter size. Okay. Okay, just a second, na. Just a second. Yeah. Now what we do now, finally you are able to construct the whole your whole grain size distribution chart. Okay, you did the sieve analysis, you did the hydrometer analysis. Now you can finally draw the complete complete your grain size distribution chart. So you have your percentage finer, you have the dia or soil size in mm. Okay. Okay, so it is a 100 and this is 0.0001. So you get the finally you get this grain size distribution chart. Now there are some parameters, related to the grain size distribution chart which helps you to decide whether the soil is well graded soil, poorly graded soil, or gap graded soil. So what do you mean by well graded soil? A well graded soil means that soil mass has equal distribution of all size of particles. Well gradation of all the sizes of particles is there in the soil mass. That is meant by well graded. Gap graded means there is some sizes of soil particles are not present. Okay, not present. That is known as the gap graded. And finally, of the poorly graded. Poorly graded means say only one size soil particles are there, or one or two sizes of soil particles from the soil mass. This is the poorly graded soil. Now, how can we find whether our soil mass is a well graded soil, poorly graded soil, or gap graded soil? This is done by the help of these quantities. Okay, the d10 size, the d10, cu and cc. D10 is nothing but the size, that is size corresponding to the 10% finer. Okay, 10% finer. This size is nothing but a d10 size. Okay, this size is nothing but a d10 size. Okay, and this is also called as the effective size. Remember that d10 size is known as the effective size. Okay, the size corresponding to 10% finer is known as the d10 size, and it's also called as the effective size. Okay, it is also called as the effective size. Then you have one more quantity which is known as the coefficient of uniformity. The coefficient of uniformity is nothing but d60 by d10. Okay, d60 by d10. And for a soil to be well graded, if it is gravel, it should be greater than 4, and it should be greater than 6 if the soil is a sand. Okay, and finally you have the cc is the coefficient of curvature, that is nothing but d30 square divided by d60 into d10, and this should always be between 1 to 3. So if these two criteria are satisfied, we can call the soil as a well graded soil. Okay, if these two criteria are satisfied, then we can call the soil as a your uh, well graded soil. Okay, otherwise it's not well graded. So we'll see, we'll use these things while we classify the soil. Okay, so in the, I don't know, I think next class or next to next, where whenever we are discussing about the soil classification, wherever we are discussing that chapter or that topic, you will see we'll use the CUCC to classify granular soils. Okay, and for so this thing, this CUCC, these are basically used to classify granular type of soil, like sandy soil. Okay, like sandy soil. Now what about cohesive soil or clay soil? So for clay soil, these things, this CUCC do not actually help us in classifying that type of soil. For that, these type of soil, we need some more parameters. Okay, some more parameters, we will see what are those. Okay, we'll see now what are those. Just a second, where did it go? Yeah. Yeah, so what we have is the consistency of clay. So clay, clayey soil can be like what to say, can be identified based on the degree of firmness. Degree of firmness means when you touch the soil, when we take the soil, clay soil in our hand, if it is flowy, like liquidy, like water, okay, it's very watery. Okay, that can be one consistency of the clay, is very watery, liquidy. Okay, the soil, it's just flowing. Okay, it is very liquidy soil. Then we have a plastic soil. Plastic soil means the soil which can be molded into any shape. You can take the soil in your hand and you can like make it a ball, make something. We can mold it in any way. It is plastic soil, plastic soil. Then you have a semi-solid soil. Semi-solid soil means a little bit water, a little bit plasticky, but little bit solid also. You cannot mold it easily. It is semi-solid soil. And finally, you have solid soil, which is, you cannot mold it in any way. It's very dry and like it's flaky, breaky, like that. So these are the different consistency of clays. Okay. Now this consistency of clays, which is defined in terms of degree of firmness, is quantified with the help of Atterberg limits. So these are very important. These are called Atterberg limits. So what are Atterberg limits? These are limits of water content which helps us to define the consistency of clay. Limits of water content which help us to define the consistency of clay. So here we are seeing a graph. So in the x-axis we have the water content, and in the vertical axis we have the volume. Now if a soil mass has a water content greater than WL, which is known as the liquid limit, the water is going to have a liquid consistency. Means it's just going to flow. Okay, it's not going to, you cannot mold it in any shape. It's just going to flow, flowy soil. Okay, if the water content of any soil is greater than WL, it will be liquid. Now, what do you do? Now you decided, I want to make a clay pot with that soil. What you have to do, you have to let that soil dry a bit. You need to dry a bit. You need to let some of the water evaporate or dry out. Then you come to the plastic region. The plastic region is between water contents WP and WL. WP is called the plastic limit. WP is called the plastic limit. So when the water content in a particular soil is between WP and WL, the soil will be plastic. That means you can mold it in any way. So potters who make very clay pots or whatever we use diyas in during Diwalis or whatever, though they actually work with the soil in this plastic region. Okay, they work with the soil in this plastic region. Okay, so at within these water contents the soil is going to be plastic. Okay, so above W well, above the liquid limit, the water is going to behave as a liquid. Between WP and W well, that means between plastic limit and liquid limit, the water is going to be plastic. So you are seeing that as you are reducing, the first the water was totally fluidy, liquidy, then we are reducing the water content. Okay, so we are letting the water dry out and we are reducing the water content. So you can see that the volume, obviously the volume is reducing, volume of that soil mass is reducing because water is going out, right? Water is drying out, evaporating, so the volume is reducing. Okay, the volume is reducing. You can see that's why the graph is coming down. The volume is reducing. Then you further dry out the soil. Then you will reach the semi-solid state. Now the water, when the water content is between Ws and Wp, the soil is in semi-solid state. And this Ws is known as the shrinkage limit. Why the term shrinkage limit? Because see, as soon as the water, you are drying the soil below Ws, you are letting more water dry out. Okay, I have reached the semi-solid. Now you are letting the more water dry out. You are seeing below Ws, the volume does not change anymore. Right, the volume does not change anymore. The volume of the water, the soil mass doesn't change anymore. It is become constant. So initially the volume was reducing and then it has become constant. Because that's why as the volume does not change, the volume does not shrink anymore. This is known as the shrinkage limit. This is known as the shrinkage limit Ws. And one more important thing that you should keep in mind is that this Ws, remember this, Ws is the point up to which the soil is completely saturated. The soil is fully saturated. Okay, the soil is fully, so this is the water content is excess, right? So here this point means water content is zero, that means dry soil. And this soil, beyond this soil, the soil, it means that the water is fully saturated. In these parts the water is partial, the soil is partially saturated. So Ws is the point beyond which the water is completely fully saturated, and below which the water, the not water, the soil is fully saturated, and below which the soil is partially saturated. So the shrinkage limit is the point below which the soil mass is partially saturated, and after which or at which the soil is fully saturated. Okay, so keep this in mind. Okay. Now, how to determine? So you had taken your some soil in your hand, right? From outside, you took some soil. Now you want to measure the liquid limit, this liquid limit and plastic limit. So how can we measure this liquid limit and plastic limit? So there are some tests available: a liquid limit test and the plastic limit test. The liquid limit test and the plastic limit test. So what you do to determine the liquid limit? So for this there are standard codes that are available. Okay, so what I suggest to go through, so you just to go through code one. So standard procedure you will get to know how to do that. So this apparatus that you see, so you all will be doing these experiments in your basic soil mechanics lab, okay, or basic geotechnical engineering lab. All of you will be doing this test in your college lab. All right, this grain size, this sieve analysis, this liquid limit, plastic limit, these are the basic tests that all of us do during our bachelors, okay, in the soil mechanics lab. Okay, so how to determine the liquid limit and plastic limit? So for liquid limit determination, we use this apparatus called, the Casagrande apparatus. Casagrande's liquid limit apparatus. So who was Casagrande? Do you know who was Casagrande? Who was Casagrande? Do you know? So this name Casa Grande you will encounter throughout this voices break. Oh, I understand. Maybe sometimes this internet actually fluctuates. That's why maybe the voice breaks. Okay, let me know if it breaks again. Huh? Is it fine now? So Casagrande, Arthur Casagrande, he was a like great uh, engineer who has like huge contributions in the field of geotechnical engineering. Okay, so Casagrande and you have Terzaghi. Terzaghi is obviously the father of soil mechanics. So Terzaghi and Casagrande, they have huge contribution in soil mechanics. You will be encountering their name throughout this journey of your soil mechanics. Okay, so yeah, so Casagrande actually developed this apparatus to determine the liquid limit. So what we do, we take the soil. So so there are some standard amount of soil that you need to take passing through. If I remember, you need to take some amount of soil passing through 425 micron sieve. You need to take onto soil. You need to mix it with water. You need to take some dry soil. You need to mix it in water, then make a paste. And then what we need to do, you need to just fill this container with the soil. Here we need to make a paste of the soil, and you need to fill this container with a paste of soil. Okay, so after you have done this, you need to use a tool known as the Casa Grande tool. So that tool actually looks something like this. The tool actually looks like this, or it looks like, for silty soil it is actually some, the tool looks like this. Okay, something like this. So these are the Casa Grande tools. So what we do, we use that tool, use this tool to make a groove on this, make a groove, cut a groove in the that soil paste that you have made. Cut a groove on the soil paste. Then there is a handle here. There is a handle here, the lever here, that you rotate. By rotating, what happens? This cup, cups keeps on hitting like this. The plate goes up, hits like this. So what you need to do, you need to count the number of blows. You need to count this number of blows till which the soil comes close to each other for certain amount of distance. That distance I don't remember now, but those you see in the textbook what distance should be. So here you can see that the soil has closed up certain amount of distance. Okay, so that number of blow you need to mark. So for so you have the water content and you have the number of blows. So these two you need to mark like this. So initially water content was 10%. You have number of blows, say 50. So like this, then you increase the water content, then you make another soil paste, but this time you increase the water content. Okay, you increase to 10%. Then you again count. So obviously, if with increase in water content, the number of blows are going to reduce like this. So finally you will get water contents and you will get number of blows. Okay, and if you are thinking that how will you measure the water content instantaneously, you don't do. You just put water, you change the consistency, you do the test later, because to determine the water content you need to dry the soil in the oven and do all those things. So I am not going into the detail. Those will be discussed in your soil mechanics lab when you do the experiments. Okay, but for now you remember that you need to know the water content and the number of blows required for that specific distance of soil to close in the apparatus. Then what you do, then you plot. So here we have the number of blows, and here in the this side you have the water content, and this you need to plot this side, you need to plot in the log scale. Okay, you in the x direction you plot it in the log scale. Okay, so you will get a curve something like this. So obviously when number of blows are higher, that means water content will be less. Okay, right, water content will be less. So this is how you need to plot. You will get this plot like this. Now corresponding to uh, 25 number of blows, corresponding to 25 number of blows, what you do, whatever water content you get, that is nothing but the liquid limit. Okay, corresponding to 25 number of flows, whatever water content you will be getting, that will be nothing but the liquid limit. Okay, so this is how you do the test. And for plastic limit, what you do, you plastic limit, for plastic limit you take the soil, you take some soil mass in your hand, little bit you soil you take, and then you roll it, now you need to make sure that when the soil soil mass that you are rolling, while rolling the thread that you are making, while rolling, when a 3 thread just starts to crumble, that water content you need to measure up. Okay, that will give you the plastic limit. That will give you the plastic. So these are very like it may sound a little bit absurd, but these are very effective. These tests are very effective, and these tests are done since many years. Okay, till today, these are the basic tests that are done in every soil mechanics lab. This is how it's done. Okay, so this is how you get the plastic limit and the liquid limit. So for detail, you see videos, there are many videos in YouTube. Okay, okay, you can see any one of the videos. Okay, it will be clear to you. And obviously you are going to do that. When you do that yourself in the soil mechanics lab, it's going to be more clear. Now you know the plastic limit and you know the liquid limit. So then we can define another term that is known as the plasticity index. So what is the plasticity index? IP or PI. Plasticity index is nothing but the liquid limit minus the plastic limit. Okay, so higher the plasticity index means the soil is more plasticky. Okay, the soil is more moldy, plasticky. Okay, higher the plasticity index means the soil is highly plastic. Lower the plasticity index, it means low plastic. Okay, so I have some limits. So many people have given many limits, so I will just write some. So if the plasticity index is 0, that means the soil is non-plastic. If it is less than 7, it means low plastic. If it is between 7 to 17, it is medium plastic, and if it is greater than 17, it is highly plastic. Okay, highly plastic. Okay, right, done. Now let us come to relative density. So relative density dr or id is defined as this: E max minus E natural by E max minus E mean into 100%. Now, say you have soil in a container and you want to know the relative density of the sand. You have filled sand in a container and you want to measure the relative density of the soil in that container. Now you need to know these parameters. So what is Emax? Emax is the void ratio of the loosest state. Loosest state means many words. Loosest state of the soil. That is the Emax. That is the maximum void ratio. E minimum is the void ratio of the densest state of that soil. It is E min. E natural is the void ratio of that state for which what you are measuring, where the relative density you are measuring, that state. So if you put all these quantities, you can get the relative density. Okay, relative density. So relative density greater than 85% means very dense. Then 65 to 85% means dense. Then 35 to 65 30 means medium dense. 15 to 35% means low dense, and less than 15% means very low dense. Okay. Yeah, if you have any question, you can ask.
Hello, sir, am I audible to you?
Yeah, yeah.
Yes, sir. Sir, actually, in the week 2 assignment, there are
Uh,
more questions related to, you know, like material exchange capacity and
rela-
other
related to
other
what?
terminology things
Related to?
related to base exchange capacity. Hello, sir, am
Uh,
I
uh,
audible?
uh. Yeah, yeah. Base exchange
Yes, sir.
capacity.
Uh, yes, yes. In the in the assignment 2, there are a lot of questions regarding related to cation exchange and capacity, and lightropic series. Those kind of questions are there,
Huh.
but those are the things not related to our civil engineering. No, as we civil engineers, we more concerned about the engineering properties, right?
Yeah, yeah, yeah.
But
Those,
still, there are a
see,
lot of
see,
questions.
yeah,
Yeah,
yeah.
yeah.
See, these are just the some basic things that some questions that are given just for the sake of completion. Okay, because in every soil mechanics course, whenever it's taught, the basic first chapter
Mhm.
consists of this ionic property. So, see, if I open, all of you might be having this book, right? This basic soil see, this basic soil mechanics book you might be having, right? So if you see, we'll
Mhm.
see, um, all these textbooks initially begin by like this chapter only, these things, these topics only. Okay, so that's why just for the
Sir,
sake of
which,
completion in one assignment it's given to you, nothing to worry about.
but sir didn't teach anything related to base and exchange capacity, right? So that's why
So
we are
okay,
facing so
okay,
many
okay. So
problems.
what? Okay, so what I suggest you is that you go through this book, a Basic and Applied Soil Mechanics by Gopal Ranjan and ASR Rao. You go there and you go to this chapter. Let me tell you. Just a second. Soil structure and clay minerals, the fourth chapter. Okay, there you will find sufficient information that that amount of information. If you read that, you will be able to solve all the questions easily. I am 100% sure. Okay, there's nothing very complicated there. Okay, if you just go to this soil structure and clay mineralogy, this see, yeah, this chapter, if you go and look, have a look in this chapter, you will get the, I think maybe the questions are, maybe some you will get direct answers also, you might get. I'm not sure, but you might get. Okay, so nothing to worry. I know because every year this course is run, and every year some questions. I don't think many questions, but some questions are given from this chapter for the sake of completion. You don't need to worry about. These are, I am sure that these are very simple questions. So just go through this. Go through the example problems in this chapter in this book, Basic and Applied Soil Mechanics by Gopal Ranjan and ASR Rao, that fourth chapter, soil structure and clay mineralogy. If you go through the example questions in that book, I think you will be able to solve the questions that are given in your assignment. Okay, so when is the
Thank you,
date
sir.
of submission of this assignment?
February 5th.
Wednesday, February. Okay, you have time then.
February 5th.
Okay, okay, you have time then. Okay, just I think I haven't seen the questions, but I am sure that these basic questions will be related to whatever is get discussed in the chapter only. So just go through the chapter by yourself, see the example problems, and see if you're, whether you're able to solve the problems. Okay. Okay, and if you are not next class, we can discuss, because today I cannot discuss or I can help you with that assignment, which is pending in the next week. Okay, today I have to focus on the week one itself. Okay, and that is not that important. Okay, if you don't, those are very basic. Those are related to chemical engineering mainly, like chemistry and all. So that is not that important. You are right, it is not that important for you. But just for the sake of completion of the course, those problems are given. And if you go through the chapter, if you go through the example problems from the whatever I told you, Basic and Applied Soil Mechanics book by Gopal Rajan and ASR Rao, you will be able to solve that problem. I am sure. Okay. Yeah. So how much we have we will solve some problems very fast. Okay. We have 45 minutes now. What we are going to do? We are going to solve some problems. Okay. And please keep your calculators with you. And I want you to also solve the problems yourselves and tell me the answers. Okay. I will be solving obviously, but I want you to also solve with me. In that way, it will be beneficial to all of us. Otherwise, if you just keep on hearing me and seeing the this lecture, you will get bored. Okay, we lose interest. Okay, but if you keep your pen and paper with you, have your calculator with you, you keep on doing. Okay, so it will be competitive and it will be more interesting that way. Okay. Yeah. So let us solve some easy problems. Yeah. And yeah, you don't need to address me as sir or whatever. You can directly call me by my name. Okay, Ashish. It's perfectly fine. You can call me by my first name. Uh, yeah, because this is not an formal discussion. Okay, it's very informal, and I expect that you also contribute equally to this discussion. Okay, so let us start. So let us see this question. A soil sampler of volume 1000 cc is used to collect soil samples. It was found that the sampler contains 2 kg soil with dry unit weight of 1800 kg per meter cube. Okay, if 100 gram water is 400 gram water is mixed to the soil, then what will be the water content of the sample? Okay, so try to calculate, try to do this. Just try to start. So the question is, soil sampler of volume 1000 cc, means the volume of the sampler is 1000 cc. Uh, okay, you are saying it's how much? Okay, okay. Let us see. Let us see. We'll solve it. We'll solve it. 11.11 you are saying water content. Okay, let us see. We'll see, huh? So first let us write down whatever it's given. Okay, so what is the dry unit weight? Dry unit weight is 1800 kg per meter cube. This is given to us. This is the dry unit weight of the soil that is given to us. Now we are asked to find out the what? Water content, right? So water content, what is water content? Please what tell me what is water content first. What is water content? Water content. Water content. What is water content? What is water content? No, I'm not asking the answer. I'm asking you the this how do you define water content? How do you define water content? How do you define water content? We studied this in this class only, right? Weight of water by weight of solids into 100%, right? Weight of water by weight of solids, correct. Fun, correct. Okay, weight of water by, so we need to know the weight of water and we need to find out the weight of solids. So weight of water and weight of solids, these two things we need to find out. Now first let us find out the weight of solids. So how can we find out the weight of solids? So we have the dry unit weight, right? Dry unit weight. Dry unit weight means what? It the weight of solids, because there is no weight of water, no weight of air, the soil is dry. Thus there will be the weight of solids. Okay, weight of solids divided by the volume. Divided by the volume. Now so we can write gamma d times the volume, right? Weight of solids is nothing but gamma d times the volume, correct? Now what is gamma d? Gamma d is 1800, and what is the volume? Is 1000 cc minus 6, so it will be 1.8 kg, right? So I have a sampler, that means I have a container. In simple terms, I have a container of 1000 cc. I have a container of 1000 cc. Now that container has a soil. In that soil mass, I will have soil solids, I will have air, I will have water, right? And the volume, combined volume is V, that is 1000 cc. Now how do I get the volume of solids? I have air, water, soil, right? The total volume is 1000 cc. 1000 cc. I want this weight. How can I find out this weight? If I multiply gamma d with the total volume, I will find out the this weight of soil solids, right? So I get the weight of soil solids as 1.8 kilograms. Okay, now let us see. Now, if the weight of soil solids is 1.8 kilogram, tell me what will be the weight of water. If the weight of soil solids is 1.8, what is the weight of water? See the question and tell me. If it was found that the sampler contains 2 kg of dry unit, so this total weight, whatever this total weight is 2 kg. So how much is the weight of water? How much is the weight of water? Very easy, right? Weight of solids you know, total weight you know. You need to find out the weight of, correct, zero point 0.2 kg, correct. Yes, yes, zero point 0.2. Yeah, 200 grams, correct. 0.2 kg. So weight of water is nothing but 2 minus 1.8, nothing but 0.2 kg. Okay. Now let us come to the second part of the question. If 400 gram of water is mixed to the soil, then what will be the water content of the sample? So now the final water content will be what? 0.2 plus, now again 0.4 kilogram of water is added, so 0.6. So this is the final weight of water, right? So therefore the water content is going to be 0.6 by 1.8 into 100%, which is nothing but how much? 33.33%, not 11.11%. Okay, the answer is 33.33%. Okay, I hope this is clear. Okay, now next question. Okay, an oven dry soil has a specific gravity 1.5 gram per cc. If the bulk density of the soil in natural state is 2 gram per cc, then what is the water content of the soil in its natural state? So if a dry density is given, okay, so dry density is given as 1.5 gram per cc. This is the dry density. Okay, the dry density is given. We need to find out the water content of the soil in natural state. How to do this? How to do this? Try to solve. Try to think how can we solve this? Bulk density is given. Okay, that means gamma t. So unit weight is given as sigma, and gamma you tell density. When you define in terms of density, that times you write sigma. Is given as what? 2.0 gram per cc. Yes. Gamma bulk is equal to gamma dry by uh, gamma dry is equal to gamma bulk by 1 plus W. Okay, not gamma bulk equal to gamma dry by 1 plus W. No, no, this yeah, no, no, no. This I think when dry will by mistake this will be density. Okay, with density. Okay, so Gautam, you have like identified correctly that we have to use this relation, but your whatever relation you have written, it's not correct. Okay, whatever relation you have written, it's not correct. So let us see that. So uh, gamma sigma t is given as 2 gram per cc. Now sigma d is sigma. Oh, okay. You what did you? Yeah, sigma d is sigma t by 1 plus W. Okay, so sigma d is 1.5, sigma t is 2.0, 1 plus w. From here w is 3.3%. Okay. Okay. Okay, it's very simple, right? Now next, consider the phase diagram shown in the figure and determine water content, void ratio, porosity, saturated unit weight, specific gravity. So specific gravity of soil is GS is given to you, and you have this figure. So please try to find out, first find out the water content. Find out the water content. What is water content? Weight of water by weight of solids into percent. So yes, 20%. Correct. 20 divided, it's given. Weight of water is given 20 by 100 to 100%. 20%. Then we have what? Void ratio. What is void ratio? Wg by S. 0.2 into 2.6 by 1.52. Correct. Again, you are correct. Yeah, porosity. Say, just use the relation between porosity and void ratio. Get 0.34. Correct. Yeah, you are right. And then finally find out the last thing, saturated unit weight also. Calculate the saturated unit weight also. So gamma t, saturated unit weight, how much you are getting? Yeah, fine only. Fine. Oh, fine, right. Fine, let us see that how to do. You are correct. Okay, Gautaman, you are correct, huh? Good. So total unit weight is nothing but G plus SE by 1 plus E into gamma W. Right? So this is the relation that we have. As the soil is saturated, gamma sat, nothing but we put S equal to 1. So G plus E by 1 plus E gamma W. Right? So we have GS 2.6 plus what is E? 0.52. You just calculated 1 plus 0.52 into gamma W. So gamma W you can take 9.81 or you can take 10, whatever. So if you take 10, it's going to be 20.53 kilonewton per meter cube. Okay, or 2.05 gram per cc. Okay. The next problem. Soil sample A and B have void ratio of 0.5 and 0.7 respectively. If 1.5 meter cube of soil sample A and 1.7 meter cube of soil sample B are to form a soil sample C having a volume of 3.2 meter cube, what is the porosity of the soil sample C? So A and B have are two soil, they have different porosities. Okay, now some volume of A is taken, some volume of B is taken to form a soil sample C. That means A and B are mixed together. Some 1.5 meter cube of A is taken, 1.7 meter cube of B is taken, and they are mixed together to form a soil sample C. Okay, now you need to calculate the porosity of sample C. Now try to do this. So can you tell me what approach you will be taking, how to do? So first let us write down whatever it's given. Okay, so for soil A, E1 is 0.5, we have V1 is 1.5. Soil B, say E2, let us write this E2. So soil C, you need to find out this, and we have V3 obviously. So how can we solve this one? So when we take two soil and mix it, what is the uh, thing that is going to remain like it is really going to get mixed. Think in that direction. Okay, so you have two soil, you have mixed them, you have got a third soil. For the third soil, you need to find out the, for that it is a mixed soil, you need to find out the porosity. Try to
Yes,
do
sir.
and tell.
We having a wide ratio so
Ah,
that we
yeah.
can bring the porosity. So we know the
Ah,
porosity equal to volume of voids upon total volume. So
ah,
we know the porosity and we know the total volume so that we can
ah,
find the volume of voids. In similar
ah,
way, we can find the volume of voids for soil B.
ah,
So on combining these two, anyway, anyhow, the volume of voids will not change.
ah. Then
So yeah, the resultant is like we can find the porosity of that sample, no?
see, try
Mm.
to check how much you are getting. See, when you take one volume A and B and you mix it, obviously, this is the void ratio will be getting changed, right? And obviously, you cannot add void ratio to void ratio, isn't it? This is not. It is not logical, right? See, you try to solve. See how much you are getting. Then you will try. You will solve it. Volume of, yeah, correct. Volume of soil solids of A you have found out, correct. Volume of soil solids for B, correct. You have found out B, correct, correct, absolutely correct. Then you are in the right direction. Then after that, so what will be the yeah, correct. Volume of soil solids, correct, exactly. 100%. Very good. You are correct. Yeah. So you got the volume of the combined soil. So yeah, the total volume you have 3.2. Correct. 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 Volume of voids, correct. 1.2. Then finally, so porosity. Yes, correct. Very good. Very good. Absolutely correct. So what we need to do is that we need to, the main thing here is that we need to have a look at the volume of soil solid. So that is the thing which is remaining constant and constant, and it's uh, going added up. It's getting added up, right? So you need to think in that direction, that our volume of solids are the thing, actually volume of solids are the things that are that are actually getting added up, right? Right, so very good. This is how we need to do it. Okay, so first what you do, we need to find out the volume of soil solids of 1, which is nothing but total volume of 1 by 1 plus e1 to 1.5 by 1 plus 0.5, get 1 meter cube, to similarly 1.7 by 1 plus 0.7 to 1 meter cube, right? Right, so total volume of solids of 3 is nothing but 1 plus 1 to 2 meter cube. Okay, and what is the total volume? 3.2. So the volume of voids of 3 is nothing but 3.2 minus 2 is equal to 1.2 meter cube. Therefore porosity of 3 is nothing but, porosity of soil C is nothing but VV3 by V3, just 1.2 by 3.2, but 0.375. Right, correct. Okay, good, very good. This is how you need to do. Okay. Okay, so then then try to solve this one next. A sampler volume of 60 cc is filled with a saturated soil sample. The specific gravity of the soil solid is 2.65. When the oven dry soil is poured into a graduated cylinder filled with water, it displaces 40 cc of water. What is the natural moisture content in the dry unit of soil? So uh, the total volume of the soil is what? 60 cc, and the soil is saturated. Okay, soil is saturated. The total volume is 60 cc. The specific gravity of the soil solid is given to you. When the oven dried soil is poured into a graduated cylinder filled with water, it displaces the water of 40 cc. That means what? That means the volume of soil solids. The volume of soil solids is 40 cc. Oven dried soil means what? Only soil solids are there, and that when you put into the water it displaces 40 cc of water. That means the volume of soil solids is 40 cc. Fine. The volume of soil solids you have, total volume you have, specific gravity you have. You need to find out the moisture, natural water content, and the dry unit weight. Okay, so do this. Volume of soil solids you are having, total volume you have the gs, that is the specific gravity of soil solids. Okay, so try to solve this one. This one is also very simple. Okay, so you need to use your basic relations of index property. So if you have gone through the class and gone through the textbook, you will do. Yeah, correct. 18.86. Yeah, correct. So let us see how you have built it. Okay. So I want all of you to answer. Okay. Answer. Okay. Everyone, please try to answer. Okay. All of you must contribute. Okay. So as I said, total volume is 60 cc. Volume of soil solids. Yeah. Volume of soil solids is equal to 40 centimeter cube. Okay, so what will be the volume of voids? Total volume minus volume of solids, but 20 centimeter cube. Now what is the void ratio? The void ratio is volume of voids by volume of solids, but 20 by 40, 0.5. Therefore now we have the soil is completely saturated, so S is 1, gs specific gravity is given as 2.65. Therefore we have, you can use the relation Sc is equal to water content into gs. This relation you can use. So water content is Se by gs 1 into 0.5 by 2.65 will have 18.86%. Okay, and yeah, gamma d, yeah, correct, gamma d is 1.7. So again we will use the relation that we used before. Gamma d is equal to gamma t by 1 plus this. So gamma t is what? You can write g plus ac by 1 plus e gamma w. So g plus e s is equal to 1 plus e gamma w. I can take 1 gram per cc. So 2.65 plus 0.5 is equal to 2.1 gram per cc. Therefore gamma d is 2.1 by 1 plus 0.1886 equal to 1.76 gram per cc. Okay, so please take care of the units. Okay, please take care of the units. Huh? Don't make mistake with the units. See when you are using kilonewton per meter cube. See when you are using gram per cc. Okay, take care of the units. Else problems are simple itself, right? So first, what did we do? We found out the water content. We know the volumes. We found out the void ratio. Using the void ratio and the relation S is equal to W into G, we found out the water content. Then we use then we calculate the total unit weight or the bulk unit weight, and then use this relation to use by relation to get the dry unit weight. Okay. A compacted cylindrical specimen of 50 mm dia and 100 mm long is to be prepared from dry soil. If the specimen is required to have a water content of 15% and the percent of air voids is 20%, calculate the weight of soil and the water required in preparation of the soil whose specific gravity is 2.69. Okay, a compacted cylindrical specimen of the specimen dia and length are given to you. Okay, the specimen is required to have a water content. Water content is given and percent air weight is also given. You need to calculate the weight of the soil and the water that is required for you to put that to make that specimen. Okay, so try to find the first of all. You tell me what is the volume of the soil sample. Tell me one by one. Okay, one by one. First, tell me this. Let us go step by step. What is the volume of the soil sample? Yes. So there is nothing but the volume of the cylinder. So 4 by pi by 4 t square h, nothing but pi by 4 50 square into 100 to 196.35 cc. Correct. Now next step is what we need to do. We need to find out the uh, volume of water. Okay, so see how can you find out the volume of water. I want you to find out the volume of water in terms of the volume. I want you to find out the volume of water in terms of the volume of solids. Okay, try to do this. See if you can find this volume of water in terms of the volume of solids. Try to find out volume of water in terms of volume of solids. Okay, so volume of water some number times volume of solids. So I need to find you need you to find the relation like that. Okay, volume of water in terms of volume of solids. So what is water content? Weight of water by weight of solid. Weight of solid. Then volume of water into gamma W by volume of solid into gamma S. You can write like that. Weight of water is nothing but the volume of water times the unit weight of water. Weight of solid is nothing but the volume of solids times the unit weight of solid. So this you can write it. Now volume of water divided by volume of solids times G we can write, because uh, gamma S by gamma W is nothing but GS, unit weight of soil solid. Gamma S gamma S by gamma W, gamma S by gamma W is nothing but GS. We can write it, that's why you can write it like that. Now water content is given as 15% is equal to VW by VS into G, implies VW is nothing but 0.15 Vs into G. What is G? Specific gravity of soil is given at 2.69. Right, 2.69. So multiply 0.15 with 2.69. We will get VWS 0.4 Vs. Okay. Okay. Right. Now tell me what do you mean by percent of air voids is what by what? What is percent of air what is the ratio, what ratio to what value to what is percent of air voids? What value to what is percentage air voids? Na. What is this? How do you define Na? Just tell me this much. How do you define Na? Percentage air voids. Yeah, VAY, correct. Irfana correct. VAY V. Okay, so this is given as 20%. That means I can write 0.2. So now I have one more VA in terms of V, 0.2 V. This is one more relation that I got. So first relation I got this one, VW is equal to 0.4 Vs, and now I got Va is equal to 0.2 V. Now what is the total volume? Total volume is what? Volume of soil solids plus volume of water plus volume of air. So volume of soil solids plus Vw. What is Vw? What is Vw? zero point 0.4 Vs. We write 0.4 Vs. What is Va? 0.2 V. Right? Now if I equate the sides, I will get 0.8 V is equal to 1.4 Vs. So from here I can write Vs is equal to 0.8 V by 1.4, isn't it? Right? So 0.8 times what is V? What is the total volume? 196.35 by 1.4. So now if we do this, we will get the volume of soil solids as 1.0 to 112.20 cc. Okay, right? So this is how we got the volume of soil solids. Now what is asking the question? Calculate the weight of soil and the water required in preparation of the soil sample. I need to find out the weight of soil. Now tell me, how can I get weight of soil from volume of soil? You have volume of soil. From volume of soil you find out the weight of soil. This you should be able to do, and tell me the answer. Tell me what is the weight of soil. Volume of soil I have given you 112.20 cc. You have calculated it. Now from 112.20 cc, this is the volume of soil solids. You find out the weight of soil solids, Ws. Please find it out. From Vs you need to find out Ws. Very simple. From Vs you need to calculate uh, your uh, what Ws. Just a while back we had used this relation. See, what is Ws? Vs into gamma s. Vs into gamma s. Ws is what? Vs into gamma s. Vs into gamma s. So gamma s. Gamma s means unit weight of soil solids. I can write in terms of G. Is nothing but Gs into gamma W. Isn't it? Gs into gamma W. So 112.20 into 11, sorry, 2.69 into 1. I am calculating everything. We are calculating in gram per cc. So 130.1.829 grams. This is the weight of soil solids. Now finally what do you need to find out? You need to find out the weight of water. So what is the weight of water? 0.15 times weight of soil solids, but 45.27 gram. Okay, so this is the answer. All right, I hope it is clear to you. Okay, yeah, now let's see the next. We will have to go a little bit faster. The embankment to be constructed, the soil is to be compacted at maximum dry density of 18 kilonewton per meter cube at an optimum moisture content of 50. That means at water content of 15%, you need to compact the soil to make the dry density, and the dry density that is to be maintained is 18 kilonewton per meter. The in situ bulk density and water content in the borrow pit are 17 kilonewton per meter cube and 8% respectively. How much excavation should be carried out in the borrow pit for each cubic meter of embankment? Okay, consider G is given 2.7 and gamma we need to is asked to consider as 10. So this is a very practical problem. So generally what happens is that when we construct embankments, okay, we need to construct some embankment, okay, say road embankment or railway embankment, anything, okay. So what we need to do, we need to uh, carry, okay, we need to carry the soil from some other site. That site, it's known as a borrow pit, because when you borrow the soil from some place, a pit will be formed, right? So we call it a borrow pit. So you need to carry the soil from some other place to your site, and then you need to construct the embankment. Now the condition is that when you construct the embankment should have a maximum dry density of 18 kilonewton per meter cube at a water content of 15%. This OMC, optimum moisture content, and maximum dry density, this we will see in the compaction chapter. When we study the compaction topic, we will study all these things. At that time it will be more clear. So what are these terms, maximum dry density and OMC, optimum moisture content? This we will study later in the compaction chapter. For now, you just take it as any value of density and water content. So we need to carry soil from some place to our site to build a embankment. The embankment should have a dry density of 18 kilonewton per meter cube at a water content of 15%. This is the criteria. Now the site from where you are bringing the uh, uh, soil, that place, the soil has a bulk density of 17 kilonewton per meter cube and a water content of 8%. Okay, now it is asked how much excavation, so how much soil you should bring per meter cube of embankment. To construct 1 meter cube of embankment, how much excavation, how much soil you should bring out from there? So this is the question. Okay, so let us try to solve this. So you have Poro Pit, let us call it as 1, we have gamma 1 as 17. Okay, similar problem, okay, similar problem to what we solved earlier. An embankment dry density is given as 18 kilonewton per meter cube. W is asked to take 10. Now I can get the total bulk, I can get the bulk unit weight of this embankment, right? So gamma d2 is nothing but gamma 2 by 1 w2. So gamma 2 is 18 into 1 plus 0 0.1 5. Yeah, gamma 2 is how much? 20.7 kilonewton per meter cube. Okay. Okay, now so this is the total unit weight that you have to have for the embankment, the bulk unit weight of the embankment, that way. So we had the dry unit weight, I just calculated the bulk unit weight. Okay, now next is we can write gamma 1. It is for the borrow pit, we are writing borrow pit. G is G, I can write G to 1 plus right. So we just use this particular relation. Okay, S is equal to W into G. Okay, this he used here this portion, numerator. So this we can write. So this is 17, it is given in the question. 2.7, 1 plus 0.08, all given in the question. 1 plus E1 into 10. So from here I can get the void ratio of the borrow pit, nothing but 0. This right? Similarly, for the embankment, we can get same E2. So implies E2 is how much? 0. So void ratio for the embankment also I got. Now, again we will go back to the previous, similar to the previous problem where we calculated the voice of the solid, the volume of solids. Remember, we calculated the volume of solids. So same thing we need to do. Just a second. Yeah. So same, similar to the, I will calculate the Vs. So what you are doing, you are taking soil from one place to other place. So amount of soil from this place to the other place. So what is the thing that remaining constant? The volume of solids. So V1 Vs is nothing but V2 by 2. Okay, implies V1 is 1 plus E1 by 1 plus E2 by V2. V2, it is asked per meter cube how much volume I need to excavate, right? So per meter cube means V2 I will put 1. So for each cubic meter of the embankment, to construct 1 cubic meter of the embankment, I need to excavate 1.143 meter cube of the from the borrow pit. Okay, to construct 1 meter cube of the embankment, I need to excavate 1.143 meter cube from the borrow pit. Okay, so this is how we do, because see, the main catch here is this part is very important. Okay, because what you are doing here, we are equating the volume of soil solids. The volume of soil solids, for whatever you are carrying from there, the volume of soil, total volume might change, total volume will change, but the volume of solids of some, that volume of solid is going to remain constant, right? From one place you are taking soil, you are putting to other place, at volume of solids, that is the constant thing between these two. Here also this say 1 gram was there, here also 1 cc was there, here also 1 cc, like that. The volume of soil solids never changes. The volume of soil solids never changes. Total volume might change because the void ratio might change, the water content might change, the what to say, the density may change, but the volume of soil solids, when you are transferring from one to here, that remains the constant thing. Okay, so this is how you do it. So this is the main concept here, main conceptual part here, this thing. Okay. So next question, relative density test was conducted on a sandy soil. The following results were obtained. Emax is 0.95, E mean is given, relative density is given. Calculate the dry density of the soil. If a 5 meter thickness of the stratum is densified to how much is the, okay. So let us do one by one. So first, let us see. I will do it a little fast, okay? Because 8, 9, 10, 11, 4 problems we need to solve. We don't have time, so I will do a little bit fast. So IT is E max minus E natural by E max minus E mean. Now relative density is given 45%, 0.45 is E max is 0.95, E mean let us E natural let us write is E 0.95 minus E mean is given as 0.40 here. Okay, so I get the void ratio as 0.70. Now it is given calculate the dry density of the soil. Okay, then you have to calculate the dry density of the soil. So gamma D is G gamma W by 1 plus E, 2.7 into 1 by 1 plus 0.7 is nothing but 1.588 gram per cc. Okay, done. Dry density of calculated. Now next part of the question is if a 5-meter thickness of the stratum is densified to a 70% relative density, how much will the thickness? So 5 meters, say the height is 5 meter, thickness is 5 meter. Say other as this is 1, the out of plane thickness is also 1, let other things everything is 1, the height is 5 meter. Now obviously when you densify the soil, when you make it more dense, the this is going to reduce like this. There is going to be some reduction in the volume, there is going to be some reduction in the volume of the soil, right? When you densify there will be some reduction of the volume, right? Now you have to find out that thing. Now see, now for 70%, for 70%, if I need to calculate the natural void ratio, what will that be? 0.95 minus E dash, let us write it as 0.48 implies E dash is nothing but 0.565. So for 45% relative density, the void ratio is 0.7. But for 70% relative density, the void ratio is 0.565. Okay. So if anyone wants to leave, you can leave. There is no problem. Okay. If you have some work, you can leave easily. I will just finish the 2-3 problems, then I will end it. And the recordings will also be made available to you. So there is no issue. If you want, you can leave because it's already 8. Okay. I don't want you to have any inconvenience. Okay. I don't want you to have any problems. Okay. So if you want, you can easily leave. There is no issue at all. Okay, the recordings will be made available, so you can see this last two problems later. Okay. so yeah, so point 0.7, for point 0.7 I have a void ratio of 0.565, right? Now initially the volume, let us take it as 5 into 1 into 1 is 5 meter cube. Okay, now the volume is reducing, right? So when I compact it further, the volume is going to reduce. When I densify it further, the volume is going to reduce. So now E is what? Volume of voids by volume of solids. This like volume of voids I can write as what? V1 minus Vs by Vs. From here, if E is 0.70, I can get Vs as 2.94 cube, right? And V1 is this one, right? Now similarly, E dash is equal to V2 minus Vs by Vs. Okay, now Vs I have 2.94, 2.94, and this one I have 0.565. So now I can get V2. V2 is 4.601 meter cube. Therefore, the reduction in the thickness is 5 minus 4.601, nothing but 0.4 meters. Okay, this is this much, approximately 0.4 meter thickness is reducing when you densify the soil from 40% to 70%. Okay. So find the liquid limit of the soil from the data obtained from a liquid limit test conducted using the Cassagrain apparatus. So as I said, you will have number of blows and you will have a water content. So then what you need to do, you need to plot it like this. Okay. So number of blows and you will have the water content. But this time log scale. You need to plot in the log scale. So we'll get something like this, a line like this. Okay. For corresponding to 25 blows, whatever water content we have, that is nothing but the liquid limit. Okay, and the slope of this line is known as the flow index. Okay, slope of this line is called the flow index. Okay, so this I plotted for you in Excel. So this is the thing, this is how the points you get. So what you can do, you can approximately, you can draw a line something like this you can draw. Okay, like this you can draw, and then corresponding to your 20 sorry, corresponding to 25 you can find something like this. You can find it from here. 25 flows will get, so approximately the water liquid limit comes out as 70%. Okay, so like this you need to, it's just for just to show you why I had put this one, nothing else. Huh? Right, so almost last two problems, problem 10 and 11, let us see, then we will close the session. Okay, an overnight soil sample of 200 cc weighs 360 grams. If the specific gravity is 2.7, determine the void ratio and shrinkage limit. So I will do that. So overnight sample, so dry weight is, dry volume is 200 cc, soil solids is 360 grams, gs is 2.7. So gamma d is nothing but wd by vd. From here ws is nothing but ws by the w dry means what, nothing but weight of soil solids wd. So 360 by 200, it's 1.8 gram per cc. So this is the dry density that you found out. Okay, now this d equal to g gamma w by 1 plus e is 1.8 is equal to 7 into 1 by 1 plus e. This relation you know, from here I can get e is equal to nothing but 0.5. So I got the void ratio. Like this I can get the void ratio, right? So dry volume is given, volume of soil solid is given, I get the dry density, from dry density I get the void ratio. Okay, very simple. Now, the interesting part. You remember, right? This was the Atterberg limit chart and this is the shrinkage limit. This is the water content and this is the volume. Now, I told you one thing, right? At shrinkage limit, till shrinkage limit, the soil is what? What is the saturation of the soil? Is it 0? Is it 1? What is it? At shrinkage limit, what is the saturation of the soil? Is it fully saturated? Is it dry? Or is it partially saturated? Tell me this. Is it fully saturated at shrinkage limit? The soil is fully saturated, dry, or partially saturated? I want the answer of this question. At shrinkage limit, what the soil is fully saturated? Correct. Absolutely. Correct, Mr. August. Correct. The soil is fully saturated. Okay, the soil is fully saturated. So, at shrinkage limit, the saturation is 1. Now we have SC is equal to WG. We have this relation. Now this water content is SC by G is 1 into 0.5 by 2.7 equal to 0.185. This is nothing but the shrinkage limit WS. Okay, this is nothing but the shrinkage limit. So we know the volume here, right? This dry volume we knew. This dry volume is going to be the same as the volume at shrinkage limit. From there, I got the void ratio at here at this. From void ratio at here, I got the void ratio because these are going to be equal. So that I used to obtain the finally the shrinkage limit. Okay. The last problem. The specific gravity of a fully saturated specimen of clay having water content of 40% is 1.88. On oven drying, the mass specific gravity drops to 1.74. Calculate the specific gravity of clay and its shrinkage limit. So I will do this very fast. So mass specific gravity, not the specific gravity of soil solids. Here mass specific gravity is given. It's total unit weight by unit weight of water. It is saturated, so I can replace total by saturated. Right, now also saturated unit weight is equal to what? G plus E by 1 plus E gamma W. So this I can put here, substitute here. So what I will get? Gm is equal to G plus E by 1 plus E into gamma W by gamma W, right? So from here I can get G plus E by 1 plus E is equal to plus 1.88 is equal to G plus E by plus E. Okay, now what is E? E is what? E is W into G by S. Okay, W into G by S. So S is 1. S is 1. So I can get write it as 0.4 G. E is 0.4 G. This 0.4 G I can put here. We'll do it here. G plus 0.4 G by 1 plus 0.4 G to 1.88. So I get GS 2.9. This G is nothing but a GS. Okay, the specific gravity of soil solids. I will write GS. Then it will be easier for you to differentiate. Okay, GS, 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 GS. So you get GSS 2.9. Now Gm is gamma T by gamma W, which is nothing but gamma D by gamma W. I get gamma D by gamma W is equal to 1.74. So this I get one more relation. Now I can write G is equal to. So this is one relation for relating shrinkage limit to your G and everything. You can remember this. Okay, shrinkage limit. WS is nothing but a shrinkage limit. But this one you can, this relation you can remember. Okay. From here if I put 2.9 is equal to 1 by this ratio I have 1.74, so 1 by 1.74 minus Ws by 100 will get the shrinkage limit as 23.10%. Okay, so this relation you can remember, huh? This particular relation, Gs is equal to 1 by gamma W by gamma D minus Ws by 100. Okay, this relation you can remember. So like the so using that we calculated the shrinkage limit. All right, so with this we'll end today's session. Thank you so much for attending. This will be here, this whatever we solved, this file, this PDF file will also, you will get the link for the PDF files also, PDF file also of the solutions, everything you will get, and also the link for your this recording of this session, that also you will get again, so that you can have a look at it anytime you want. Okay, again and again. Okay, so with this we'll end today's session. Thank you so much for attending. Have a great evening, good night, and take care, and see you next Monday. Okay, so next Monday same time, 6 to 8 p.m. again we'll be trying to solve some simple problems. Okay, thank you so much. Thank you for attending. Have a good night. Thank you, take care. Bye bye.